Welcome to Study Loop.
Hello everyone, today we're doing chapter 17, problem 14, and this problem gives us this molecule here and asks us a few things. Number 1a, it asks us to explain why the 5-member ring in this molecule is aromatic. So explain why this ring here is aromatic, the 5-membered ring is aromatic. B, it asks, determine the hybridization of each nitrogen atom, and C asks, in what type of orbital does each lone pair nitrogen atom reside? So let's determine first why this 5-membered ring is aromatic. So remember, in order to be aromatic, we need to follow Huckel's rule 4n plus 2, where n can be any positive integer. And this 4n plus 2 rule is corresponding to the number of pi electrons, or the number of electrons in the p orbital. So we can have a possible of 2, 6, 10, 14, etc. Electrons in a pi or p orbitals to be an aromatic compound. So let's look at this cyclical structure. So what do we know about nitrogen? Well, we know that these nitrogens have 3 bonds, but then each of these have lone pair electrons. So let's look at this nitrogen on top. Well, this nitrogen, A is asking for why is this compound aromatic? Well, we know that in order to be aromatic, we need to have either 2, 6, 10, or 14 pi electrons. Well, let's see this structure here. Well, we know that 2 electrons are being donated by each pi bond. So 2 electrons here, 2 electrons here. But now what about this nitrogen here? So remember, in our previous question that we did, we determined that if we have some sort of molecule, if you have molecular orbitals coming out of this, nitrogen will make 3 molecular orbitals, and then we'll have, so these are the sp orbitals, these black ones here are sp orbitals. Then we can have your p orbital that's coming up and down. So imagine these black ones are flat on your page, and this blue orbital, the p orbitals, is coming up and down through the page. So you see that they're actually perpendicular. So here in this nitrogen, we have those 3 molecular orbitals, which are all your s orbitals to make those single bonds or sigma bonds. Then we have that lone pair electron. That lone pair electron actually is going to reside in that p orbital that goes up and down. So because it's in that p orbital, it can actually delocalize into the ring and actually be counted for aromaticity. So including these 2 electrons, we have 1, 2, 3, 4, 5, 6 pi electrons. 2 electrons are from each of these pi bonds, and the last 2 electrons are from the nitrogen atom that is not part of the double bond. So we know that this molecule is aromatic because it follows the 4n plus 2 rule with n equaling to 1, and that's because this nitrogen that was here behind all these drawings, this nitrogen actually has a lone pair electron that exists in the p orbital and not in the sp orbital. So because these 2 electrons exist in the p orbital, they're able to delocalize into the ring and be involved in aromaticity. So another trick you can determine if your pi electron, or if your lone pair electrons will be in the p or sp orbital, is that if you have an atom, such as this nitrogen, that has multiple bonds attached to it, well then its lone pair electrons cannot be involved in determining aromaticity. So for example, these 2 nitrogens have already multiple bonds attached to them. They have pi bonds to them, double bonds. Therefore we know that their lone pair electrons cannot be involved in determining aromaticity. They're in an orbital in one of these black sp orbitals here. So because of that, this nitrogen on the top, we know that it has no double bonds attached to it, so that we know that right off the bat, yes, these 2 electrons can be involved in aromaticity because they can exist in this p orbital. So let's see what B is asking. B is asking to determine the hybridization of each nitrogen atom. Well, remember the hybridization, we have sp. S max can be to the power 1, P max can be to the power 3. And the reason for that is, for example, if we have a carbon atom, well, carbon atom, if it's bound to 4 things, then we need 1 plus 3 equals those 4 things it's bound to. We have 4 hydrogens. So then this carbon is what we call an sp3 carbon. But now what if we have a carbon that looks like this? Well, we have one group on the left, one group on the right, and this double bond to oxygen is considered as one group as well. So in essence, we have three things bound to the central carbon. So we have s to the power 1, and we need two more things to equal 3. So we have p2. So this carbon would be an sp2 carbon. So using that same logic, let's move on to these nitrogen atoms. And we can actually answer B and C together. So what's the hybridization of each nitrogen atom, and what orbital does a lone pair on the nitrogen exist on? So we already kind of answered for this nitrogen that the lone pair is going to exist in the p orbital for this nitrogen. Why? Well, because we know that this nitrogen has 1, 2, 3 things already bound to it. So because it has 3 things, this is an sp, s to the power 1, so we need 2 more things, so sp2 hybridized nitrogen. And because of that, we know that nitrogen is fully satisfied in its hybridization, so those 2 electrons can actually exist in the p orbital to be delocalized into the ring. Well, now what about these 2 nitrogens here? So if I were to just erase these red around it so we can clearly see, so if I were to just redraw this so we can just clearly see this, so this nitrogen has a double bond, nitrogen, and a lone pair electron. Same with this nitrogen. This nitrogen has a double bond, nitrogen, lone pair electrons, and these nitrogens are bound to each other. So if we look at this nitrogen here, and actually I can draw this outside of the ring just so we are very clear with what we're looking at. And then this nitrogen had one more bond here, and then we'll just ignore the rest of the molecule. So we determined that this nitrogen is sp2, the top one, and its lone pair electrons exist in the p orbital. Well, what about this nitrogen on the right? This nitrogen on the right has one group on the left, one group on the bottom. So we would say it's an sp hybridized nitrogen, but no, nitrogen does not like to be sp. It needs to satisfy its maximum hybridization. So this lone pair electron that's actually here is actually going to occupy one of the sp orbitals. So in this case, these 2 electrons, this lone pair electron, is actually going to exist in an sp orbital. So we can say that we have 1, 2, 3 things attached to this nitrogen. So we have an sp2 nitrogen. And we know that right away it does not occupy the p orbital because this nitrogen is already bounded to a double bond. Because it has multiple bonds attached to it, these lone pair electrons cannot exist in the p orbital and cannot be involved in delocalization and aromaticity. So therefore, we know that these lone pair electron here is in the sp orbitals. And not only that, well, we know that this nitrogen can nucleophilically attack things with its lone pair electrons and pick up protons, for example. And then actually, to emphasize that point, let's look at this amino group here. Well, this amino group has a lone pair electrons, and we know amino groups can actually act as bases and pick up protons. Well, in order to pick up a proton, this lone pair electron has to exist in its sp orbital. But in order to pick up a proton, then that means that if it were to pick up a proton, this nitrogen would now have 3 protons and then be bound to its group up there. So that means this nitrogen now has 4 things. So this nitrogen is actually an sp3 nitrogen. Because of that ability for that lone pair electron to pick up extra substituents, we know that it's going to exist in one of the sp orbitals. So then we would have 2 hydrogens, 1 bond to this carbon, and 1 substituent being these electrons. So we have 4 different things attached to it. So it would be an sp3 hybridized atom here. So now on to the last carbon. This carbon down here, we have a nitrogen, sorry, not carbon, a nitrogen. So we have a nitrogen here that's double bonded to a carbon, single bonded to a nitrogen. So we have, in essence, let me do it in green, we have 2 substituents here. 1 double bond, 1 a single bond. But we know that because nitrogen is involved in a double bond, this lone pair electron cannot be in a p orbital. So that means it must be in an sp orbital. So we know that the lone pair is actually going to be in an sp2 hybridized orbital because we have three things attached to this nitrogen, one of those things being that lone pair electron here. So it may be kind of confusing. Well, why are these two nitrogens sp2 with their lone pair electrons existing in sp2 hybridized orbital, while this nitrogen here is sp2, but its pi bond is its lone pair electron is existing in the p orbital? Well, because of the reason for that is because these two nitrogens here have double bonds attached to them. So when you have double bonds attached to them, your lone pair electrons cannot be involved in your sp orbital, so that by default they must be in the p orbital. So that explains why these two nitrogens here have electrons that are not in the p orbital, because they have multiple bonds attached to them. So right off the bat, we know they must be in sp orbitals. But because this nitrogen here has no double bonds to it, we know that these lone pair electrons can actually exist in the p orbital and not be involved in the sp orbitals. But here we also have a nitrogen that is not involved in any multiple bonds, but the only difference is that this nitrogen here actually has no conjugation around it. So we don't have any double bonds around it. So it makes no sense for these electrons to exist in the p orbital to delocalize, because delocalizing wouldn't do anything for the molecule. It is better for these electrons to exist in the sp orbitals, so then the nitrogen can use this lone pair electron to nucleophilically attack stuff like picking up protons or attack electrophiles to add an extra substituent. So then this nitrogen would end up having 4 substituents here.